All right, hey guys, we're going to start a new topic in geometry now. You should have a new packet to grab from that hopefully you got a textbook pickup. But right after our area, perimeter, and circumference page, on this next page, we are looking for the packet that says reasoning and logic. And if you don't have it, it's going to be linked at the top of Google Classroom under our classwork tab. So hopefully you can find that and print it if you're able to. Okay, so this is going to be our little divider if you remember before. So I'm going to kind of divide this in a third here so that I can see the little tab that says reasoning and logic. And we're going to tape it or glue it around this next page. So like the short part goes on the front and the long part goes on the back. And I like to have mine poke out a little bit so that it does work like a divider or a tab that I can see on the outside of my notebook. Now, when it comes to this topic, reasoning and logic, this is really sort of the basis of how math was built and kind of like how it was formalized, if you will. Like a lot of people were using a lot of math back in the day, like way back in the day, but it wasn't formalized. Like it wasn't in a textbook or it wasn't in a book, or people just kind of did it the way that they wanted to do it. And for the most part, they were kind of doing it correctly, but they wanted to come up with rules that everybody had to follow and that everybody could learn from. And that just made sense, like logically. So we're going to be talking a lot about logic. And the first page that we're going to do today, we're going to put in our table of contents right here. We are going to talk about conjectures and counterexamples, which we talked about counterexamples in class today. So we're going to just do this, and we are on page 15. We're just going to do this on page 15 because I don't know that we need another page for it. Okay, so right across from that, we're going to call this page 15. And it should be the next notes in your notebook. It should say at the top, conjecture, inductive reasoning, counterexample. And if you flip it around, we're going to fold it to the middle so that we get our little French doors like this. And then if we want to cut to make some doors, that could be really cute and fun. And then tape it down. So when it comes to math and science and like research, like historical research or whatever sort of research you're going to do, it's really important that we use deductive reasoning. So we base our new facts on old previous true facts, okay? However, sometimes it is important for us to use what's called inductive reasoning, where we look at a bunch of examples and make a guess. It's not going to prove that your guess is true, but it's a good place to start, where you can look at these patterns happening and sort of make a guess or make a conjecture about what you think is true always. And then you have to prove that it's true, which we're going to get into that much later. But then we can use that true fact to make new true facts, and that's when we use deductive reasoning. And again, we'll get to deductive reasoning stuff later as well. Okay, so inductive reasoning is using a number of precise examples to arrive at a conclusion. So we're using specific examples to make a guess about what we think is happening. We don't know for sure because we can't see everything here. And so a really good way to show inductive reasoning is with a string of numbers. Like if I see these numbers changing, so 2 to 5 to 8 to 11 to 14, I might make a guess that what is happening is that we are adding 3 every time. And that could be the case, but I don't know the rest of the numbers, and eventually they could change and not do that anymore. So inside here, you're going to want to make a conjecture about the pattern and then list your next term. Now I'm going to do it, but if you want to try to sort of do it first and then come back and check to see how you did, I think that could be a really good idea. So maybe pause the video and try these out where you guess about the pattern and the next term, and then come back and check to see if you're right. That could be a really smart idea. So if I look at this first one, we have, this is 5. Okay, I thought I got chopped off here. 5 to negative 10 to negative 25 to negative 40. This one looks like it is decreasing. So I'm going to say subtract 15. That does seem to be the case. If I do 5 minus 15, I'm at negative 10, minus 15 more, minus 15 more, which means that your next term, if I subtract 15 again, would be negative 55. Okay, this next one here, that's what got chopped off, the 1, 1, 2, 3, 4. We start at 0.25 or a fourth, and then I'm at 1, and then I'm at 4, and then I'm at 16. So this time it doesn't seem like you're adding something. I think we are multiplying by 4. Like a fourth times 4 is 1, 1 times 4 is 4, 4 times 4 is 16. And so then the next term, 4 times 16, would be 64. And you can see that that one's growing a lot. Okay. Number 3 down here, we got 25, 5, 1.2, which is actually 2/10 or 1/5. And so I think this is very similar to that last one where, I mean, it's not growing, it is shrinking, but it's shrinking at an increasing rate. So we're not just adding or subtracting. I think we are dividing. That goes faster by 5 every time. Like 25 divided by 5 is 5. 5 divided by 5 is 1. 1 divided by 5 is 1/5 or 0.2. So your next term, if I were to divide a fifth by 5 again, because I'm dividing the 5, it goes under. So for me, the easier way to say it is 1/25, because 5 times 5 under, which as a decimal is 0.04. Yuck. And then this last one is very interesting. If you tried it on your own, I'd be so interested to know if you got it. But we went from 1 to 1 to 2 to 3 to 5 to 8. And really what's happening here is we add the 1 before it. And what I mean by that is 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 means that the next is 13. And this is actually a very famous sequence called the Fibonacci sequence. So that's kind of cool. Now, once we have our inductive reasoning, or once we've kind of made a guess, if we want to formalize that guess, we write it in what's called a conjecture. Okay, so our conjecture is the concluding statement based on your reasoning. So in these examples here, we would say the next number is, and using the front example, so using a number of precise examples to arrive at a conclusion, since we're adding 3 every time, that would mean that the next number is 17. So to write a conjecture appropriately, usually you want, if I add 3 every time, then the next number will be 17. So if, then is the proper way to write a conjecture, where if this thing continues to happen, then this thing will be the conclusion of that. So if we look at some examples under here, make a conjecture about the geometric relationship. Again, this could be a good one where you maybe try some, and I don't know if I'm going to do all of these, but try and then maybe come back and check to see how you did. So number 1, angle MNP is a right angle. Well, if that's all I know about it, I could say that if it's a right angle, then the measure of that angle will be 90 degrees. That's something that I definitely know for sure. That's what it means to be a right angle. We could do all these. We got time. Number 2. So if the measure of angle A plus the measure of angle B is 90, then a true fact that I know about that is that means they are complementary. So angle A and angle B are complementary. We're really just trying to think about a true fact that we can say about what they've told me so far. Complementary. Spelling. Okay, number 3. Point B is in between points A and C. Oh, this is one that we've done, right? So if point B is between A and C, then I know that I can do some segment addition. And the segment addition said that we could add up the two smaller parts. So B being between these, AB and BC would be the smaller parts, and we'd have the whole line, AC. Okay. Number 4, triangle DEF is equilateral. Well, in that case, we have to understand the definition of equilateral, so hopefully you do. But if triangle DEF is equilateral, then we could say all sides are the same. Or if you wanted to be really fancy about it, you could even write it out as an equation, like DE equals EF, which equals DF. And you might know something else about if you're equilateral. So there could be another thing you could say here, but that's the most obvious. So that's all for now. Number 5, angle ABC and angle CBD form a linear pair. Well, we understand the definition of a linear pair means that these angles will add up to equal 180. Because if I make a linear pair, then I make a line or a straight angle, and a straight angle is always 180 degrees. And then last but not least, points D, E, and F are non-collinear. So if I have 3 non-collinear points, then I have a plane. That's the definition of a plane. So points D, E, and F are non-collinear. I would say they create a plane. Now, if you don't see a pattern, or if you know for sure that something breaks the pattern, then you want to use that thing as a counterexample to your pattern, okay? It's much easier to find a counterexample than it is to show that something is true all the time, because I can't show every example. We have to use these proof methods that we'll talk about later to show that something is always true. So that's why it's always important to try and show that something is false first. Okay, so if I can find a false example to show that a conjecture is not true, then I've found what's called a counterexample. So for instance, the sum of any 2 integers is positive. Well, that's false, because if I take 2 integers, let's say -2 and -5, those are both integers. If I add them up, that result is not positive. It's negative. So the sum of any 2 integers is positive. So you could always do that with 2 negatives, or you could do it with a really small negative, so like -30, and then a small positive number like 2, because then you get a negative as well. So as long as you can show me a specific example of this rule being broken, then you've found a counterexample. So this is my specific example to show that it is false. Another thing that is false is that adjacent angles are congruent. They for sure don't need to be. And a really good example of that could be if I had a linear pair. If I draw the line straight up, then those adjacent angles will be equal. So I don't want to do that, but I think that's the only case that it is true. If I draw a ray coming off of this straight angle, this angle right here, number 1, is adjacent to this angle number 2. However, they are not congruent. And that's the majority of the time along a straight angle. There are lots of other cases that can show that adjacent angles are not congruent, but I need them to be adjacent and then not congruent. So the hypothesis, or sort of the pattern, has to be true, but then the conclusion has to be false. So here I was adding two integers, but negative as my answer. That's kind of the tricky part. So then this last one, complementary angles create a right angle. So I need complementary angles, and I need them to not be right angles, like when I add them up, which I don't think I can do because the definition of complementary is right angle. So I think I can't find one here. That would be true. There's no case where I can have a pair of complementary angles that are creating a right angle, because they do. I guess if they're non-adjacent, maybe that's what I'm meaning here. So if I have an angle over here that's 40 degrees, and then an angle over here that's 50 degrees, and my drawing is not to scale, they're complementary, but they're not smashed together to make a right angle. Because I think a right angle has to be adjacent as well. So that's probably what we're going for there. Alrighty, so determine whether each conjecture here is true or false. If false, provide a counterexample. Again, this could be a really good one where you maybe like pause, try it, and then come back and check. So if you want to pause and try them, then come back. So number one, if angle A and B are vertical angles, then their measures are equal. That is true. That is the definition of vertical angles. So there's nothing that we can do to show that that's false. If x is a real number, then 2 times x is greater than x. I can actually show that this is false, and there's maybe lots of counterexamples that you could come up with. I feel like a good one is if I say that x is -2, which that's a real number. And if I plug that in, we'd have 2 times -2. Is that greater than -2? It sure isn't, because then I'm going to get -4 here, which is smaller than -2. So that's why that's false. I have a specific example that shows it. You have to have a specific example. Okay, number 3, if 2 lines are perpendicular, then right angles are formed. I think that's true. That is the definition of being perpendicular. You get a right angle. Okay, number 4, if 2 angles are supplementary, then they form a linear pair. So I have to have angles that are supplementary. My hypothesis must be true, but then my conclusion must be false. So I need to have 2 angles that are supplementary, add up to 180, but not form a linear pair. And that's kind of the definition of linear pair, but they must also be adjacent. So essentially, if I draw non-adjacent supplementary angles, so maybe we say that this is 110 degrees and then this is 70 degrees, they're supplementary, but they're not a linear pair because they're not adjacent and sharing a ray. So that would be false because they are not adjacent. Alrighty, number 5, if points Q, R, and S are collinear, then QR plus RS equals QS. It seems like that might be true, but I don't know for sure what order these points are in on that line. So if they go QRS, then that statement would be true. I could put it RQS, and then that statement would not be true because QR plus RS would not equal that. I have like the small piece, the whole thing would equal this smaller piece, and that is not true. So if I draw this picture here, I can see that that statement is false. That betweenness really matters when it comes to segment addition. And then last but not least here, if AB is equal to BC, so I have 2 little line segments that are equal, then B is the midpoint of AC. Again, that kind of feels like it could be true. So I just have to have 2 little line segments that are the same length, but then I have to show that B is not the midpoint of that. And to be at the midpoint, you have to be right in the middle of the line. So kind of a fun way to do this is to draw an angle where maybe this AB is the same length as this BC right here. And then B would not be the midpoint because they're not collinear all on a line. So that's a fun way to show that that is false. Another way is they could just be not or like attached to each other, or it could be like a smushier angle or something like that. So hopefully that's okay, and you try your Google form and everything goes well. Good luck.